So remember that one of the things that we started talking about was there were two problems that we started talking about at the beginning of this course. How do you find the slope of a tangent line at a point, and how do you find the area under a curve? Now that we've discussed the limits, we have the tools that we need to actually solve those problems. The first problem that we're going to solve is finding the slope of the tangent line at a point. Okay? And the tool that we're going to use to solve that is called the limit, but it creates another tool called the derivative. So whenever you hear a derivative, basically whenever you're thinking about a derivative, really what you should think about is it's something that tells me the slope of a tangent line at a point. Okay, it's just our quick way of saying that. So the derivative is a way to find the slope of a tangent line at the point. How are we actually going to achieve that? It's going to involve taking a bunch of limits. So we're going to talk about how does that work today? So let's go into writing mode. Okay, fail, my bad, don't know what happened. There we go. Okay, cool. So let's just type what I said onto the screen here. So the derivative is how we shall find the slope of a tangent line at a point. Okay, but the question is how do you actually do this? It involves limits. Okay, so you might remember that when I introduced this concept, one of the things that we discussed was how you can sort of solve the problem. Okay, what the hell is going on with my computer's going crazy. Whoa, okay, weird. There we go. Sorry. You can sort of solve this problem by looking at the slope of a secant line. Okay, because when you have the secant line, how many points do you need to make a secant line? Do we remember? Yeah, 2. Cool. So with a secant line, you have 2 points on the graph. And you're like, okay, I can do that. Now, what we wanted to do was somehow take the slope of the secant line and use it to figure out the slope of a tangent line. And what was our real issue with why were we not able to find the slope of a tangent line? We had a problem. Because it's the tangent line at a point. What was our issue? Yeah, and we were like, you need 2 points, right, to make a line. And we were like, uh-oh. What do we do? Right? Okay, so the limit actually gives us a way to do this. So I'm going to draw our graph. Okay. Here's our function, f of x. Let's say we want to find the slope of the tangent line at x equals a. Here at a. There's our point A. We would like the slope of the tangent line, which would be we'll draw a little dashed line, something like this. That's what we want, but we're not getting it. So we settle for something not quite as good, but pretty close. We choose some other point over here. And I'm going to call that point x. So now I have 2 points. I have a and I have x. And I can find the slope through those 2 points. Or I can find the slope of the tangent line through those 2 points. So, okay, why is it not letting me draw a tangent line? Okay, there we go. Thank you. There we go, in white. Right, so this here is the tangent line in blue. This here is the secant line in white. And what do you notice about the secant line and the tangent line? They're pretty close to each other, right? Like like the secant line is a pretty good approximation to the tangent line. So, what is the formula for the slope of the secant line? Well, you do the difference of the y's over the difference in the x's, correct? Okay, so what is the y value of this point right here? So what is the y value of that point? This green point right here, what is the y value? Or how about this? What's the x value of that point? Yeah, thank you. Cool. So what's the y value going to be? Not quite. The function's f of x, so literally what is the y value? Yeah, there we go. Nice, thank you. So this point right here is literally f of, x comma f of x. Okay, what about this point right here, the blue one? What is the x value of that point? Cool, so what's the y value? Not f of x, f of a. Cool, we now have our 2 points. The slope of the secant line is the difference of the y values over the difference of the x values, which means we have f of x minus f of a, those are our 2 y values, over x minus a. Boom. This has a special name. It's called the difference quotient. It gives you the slope of the secant line. Now here's the crazy thing. Let's say that you start moving this x point over towards a. If you take the limit as x approaches a of this formula, something really interesting happens. So this limit is telling us that x is going closer and closer towards a. So does it make sense? You have, this is your, let me go into this mode really quickly. Let's say this is the point A and this is the point X. X is getting closer and closer and closer to A. At the end of the, so you start with 2 points. After you take the limit as X approaches A, how many points do you actually have? So you start with 2 points, they're separate points. After you take the limit, how many points are you actually left with? Yeah, exactly. And that's what the limit does. It somehow takes your secant line and it is what turns it into the tangent line. It started off as a secant line with 2 points, but because you took the limit as x goes to a, the x point is indistinguishable from the a point after you take the limit and you only actually have 1 point. Boom. This is how you get the slope of the tangent line. Hopefully this idea makes sense. You're making the x go towards a, you're closing the gap. Like you started off with 2 points and you say, hey, let me just turn x into a. Then you're just left with 1 point. And that's literally what we wanted to find the slope of the tangent line. Okay. There's something else we need to talk about in relation to this as well. There's a slightly different way to write this formula. So we're going to redraw the drawing in a different way. So I'm going to make it like really big and easy to look at. Okay, so here's your x-axis, here's your y-axis. Here is your f of x. Hopefully you can see this really well. Here is your point A. Here is your point X. The secant line between them looks something like this. Okay. So there's your secant line. Now, when you're calculating slope, you need to know the change in x. That's this right here. And you also need to know the change in y. So does everyone see how I drew those? Does it make sense how I have that white rectangle there, right? The slope of the secant line is quite literally, let's write that right here. The slope of the secant line is delta y over delta x, right? Change in y over change in x. You take those 2 points and you get the, what are they called? The sides of a right triangle, yes? Is that mysterious? Or does everyone understand what I'm drawing here? Okay. Looks like, okay, cool. Now, let's draw in the x and y values for these points. Remember, this is x, comma, f of x. This one is a, comma, f of a. Okay, so the distance between a and x is delta x, or, okay, so we can actually rewrite x as a plus delta x. And that's how I actually sometimes usually prefer to talk about this second point. I don't want to call it x. I want to basically think of this point, this second point, as this second point is a distance delta x away from a. So I'm not going to call this second point x anymore. I'm going to call it a plus delta x, where delta x is the distance that this point is away from a. Which means that we have a different way of thinking about this blue point right here. This blue point, the second point, now we're not going to call its x value x. We're going to call the x value a plus delta x. Which means, what is its y value now? Exactly, yes. Our y value is now f of a plus delta x. Okay, so we're not going to think about this point this way anymore. We're going to think about it the other way. Okay, which actually gives us a new secant line formula. The change in y values is going to be written as f of a plus delta x, that's the first y value, minus the other y value, which is f of a. And then we're going to divide that by the x value, the difference of the x values. The first x value is a plus delta x. The second x value is just a. Now, looking at that denominator, what changes? Or what can we do with the denominator of my... Yeah, exactly. The a's cancel and we just get delta x on bottom. So we get f of a plus delta x minus f of a. This is the more common formula of the difference quotient. It's the same as the other formula I gave you above, just written a different way. And what's cool about this is that if you take the limit as delta x goes to 0, in other words, if we had 2 points, a and a plus delta x, if delta x goes to 0, what literally happens to a plus delta x? Like, if delta x goes to 0, what does a plus delta x become? A. So in other words, we end up going from 2 points to 1 point, right? And that's why if you take the limit of this difference quotient, you get the slope of the tangent line at A. Just like how if we took the limit of the difference quotient above, you got the slope of the tangent line. Why does this work? We're taking the limit and we're turning our 2 points into 1 point. Boom. Okay, so now that I've shown you the definition, we're going to do like an actual example where we use this, or one of these two versions of the formula. Does it make sense? They both give you the same answer, just sometimes it's nicer to write it one way versus the other. I prefer this second way because it allows us to think of one of the points as A and the other point as A plus something. And then you're just saying that A plus something will become A because eventually we add nothing to the second point. Okay, so let's use this to calculate a tangent line. Example: calculate the slope of the tangent line at x equals 3 for f of x equals x squared. Using the limit of the difference quotient. So I'm like basically at the problem telling you, oh, how are you supposed to do this? You do it by taking the limit of the difference quotient. Okay, so notice in the problem they tell you where you're finding the tangent line. You're finding the tangent line at 3, which means that's your A value. And your function is f of x equals x squared. So remember, the way we find the slope of the tangent line at A is by taking the limit as delta x goes to 0 of f of A plus delta x minus f of A over delta x. So your first order of business is to plug in your A value. So we want f of 3 plus delta x minus f of 3 all over delta x, right? Because we want to find the tangent line at 3. A is the value where you want to find your tangent line. We replace A with 3. That should be pretty straightforward, right? Is everyone good with that idea? Like, just the A is where you want to actually find the tangent line. We want it. We were told in the problem that we're doing so at 3. Okay, now what you need to do is calculate these two y values. How are you going to calculate the two y values? Well, they tell you what your function is. So let's do the more complicated one first. Let's do the simpler one first. Let's do f of 3. F of 3, quite simply, is 3 squared, which is 9. Hooray. The more difficult one is f of 3 plus delta x, because that's going to be 3 plus delta x quantity squared, which is going to be 9 plus 6 delta x plus delta x quantity squared. Yeah. because you might recall that a plus b squared is a squared plus 2ab plus b squared, right? So your a in this case is 3, your b is delta x, so you get 2 times 3, which would be 6. Okay. That's why, does everyone remember seeing those in like Algebra 1, Algebra 2, right? You were supposed to have, I'm not like shaming, I'm just like literally pointing out because I know that most people just forget it. Like that's like the whole point of it, because we use those things like a lot now. Okay, so you have to plug all that crap in. So you're like, okay, I've got the limit as delta x goes to 0, and my f of 3 plus delta x is literally 9 plus 6 delta x plus delta x quantity squared, and my f of 3 is 9. So hopefully you can see, like, I'm just replacing the stuff in the numerator with the calculations that I made up here. And all this is over delta x. Okay, now looking at this, this is a limit that we're going to have to compute. Why is this not looking good for us right now in terms of computing this limit? What is our problem? Like, forget about like that we're going to have to cancel and simplify stuff. Like, looking at this right now, what is our issue? Yeah, we get 0 in the denominator, right? And that's like, oh shit, like what the hell am I supposed to do, right? Because the quotient rule won't work, right? Normally we would take the limit of a quotient by splitting it up into the limit of the top divided by the limit of the bottom, but that only works if the bottom's not equal to 0. So you look at this and you're like, holy shit. Okay, so what was our method that we came up with to calculate limits like this if the bottom was going to be 0? Hopefully people have watched that far into the videos at this point. Does anyone remember what the method was? Before we go and finish calculating this. Okay, I'm gonna start writing it, maybe you can remember. I guess people haven't watched that far. Okay, we're going to have to find a function that agrees except at a point. We're going to factor and cancel to solve this limit. So what are we going to have to do? We're going to simplify. Luckily, what cancels in our thing so far? Looking at this limit in the numerator, what can I do? Actually, the delta x's don't cancel yet because we have a bunch of stuff on top. Like, you can't just go like this. There's some stuff you need to do first. Yeah, the 9s cancel. Okay, and then let's calculate this off on the side. Looking at 6 delta x plus quantity delta x squared, what can you do with that? Yes, there we go. And then we're going to be able to do some canceling. So you get delta x times 6 plus delta x. Okay, so let's write this. This now becomes the limit as delta x approaches 0 of delta x times 6 plus delta x over delta x. Okay, so this is your f of x basically now. Your f of x is equal to delta x over 6 plus delta x over delta x. You cannot solve this limit with direct substitution because that would give you 0 on the bottom, right? But you notice that this function agrees except at a point with the function you get after these are canceled, which is 6 plus delta x. So in other words, f of x is equal to g of x except when delta x is equal to 0. So in other words, these functions agree except at a point. This is a crucial step. You actually have to say this. If you don't say this, I'm going to like say you're wrong. Now, because they agree except at a point, we know that the limit of f is equal to the limit of g. So we know that this is equal to the limit of 6 plus delta x. Now, how would I solve this limit? Like, what is the method I'll use to solve it? Like, to go from here to here to get an actual number, which will be 6. What is the method I use to solve or calculate? Yeah, direct substitution, yes. And I can direct substitute because it's a polynomial, because I'm not dividing by 0. Okay, which means, what was the slope of the tangent line at 3? Yep. So 6, you have to remember what this number means. The 6 is the slope of f of x equals x squared at x equals 3, or the slope of the tangent line. Boom. That was like a lot of work to do all of that, agreed? Like, it's a lot. But we now know that if you wanted to draw a tangent line for this function at 3, the slope you need to do that is 6. Boom. How did we do that? By taking the limit of the secant line. We turned those 2 points into 1 point. Boom, we got a tangent line.